Okay, welcome to the second lecture on dimensional analysis, the fourth lecture of our course. In the previous lecture, I had taken you through the fundamental and derived quantities, and I had derived for you the dimensions of all the derived quantities that we will commonly use during the course. As I said, the fundamental quantities are mass, length, time, temperature, and then there are two that we do not really use during most of this course, that is current and dimension of light. Okay. But from these four dimensional quantities, mass, length, time and temperature, you can derive a very large number of quantities that we have employed throughout, we will be employing throughout this course. Okay. Velocity, acceleration, force, work, energy, power, pressure, stress, density, okay, and so on. Okay. Quantities which are of relevance in mass transfer, in heat transfer and in momentum transfer. Okay. So, how do we use dimensional analysis in order to analyze problems? So, we started off with the fundamental with the basic momentum transfer problem, that is that I have this tank of fluid within which there is a particle that is settling. Now, the particle is of course settling because the density of the particle is higher than the density of the fluid around it, and therefore, there is a gravitational force acting downwards. However, there is also another force due to the fluid which tends to resist the motion of the particle. As the particle is settling downwards, there is fluid flow around the particle, and that fluid flow causes friction within the particle. Okay. And due to the fluid, there is a stress that is exerted at every location on the particle surface, okay, a force per unit area, a stress. Okay. And as we know, that stress comes from Newton's law of viscosity. Okay. And this stress, this upward force exerted on the particle opposes the force due to gravity, and therefore, if I were to write a force balance equation for this particle, it would be of the form m du by dt is equal to this gravitational force minus this drag force. Okay. Our task now is to find out what is the form of this drag force. Okay. In particular, what are we have to start off by trying to find out what are the quantities, the dimensional quantities on which this drag force could depend. Okay. As I said, this drag force, okay, could be a function of, okay, first thing is it has to depend upon the diameter of the particle. Okay. It should depend upon the diameter of the particle, and it could also very well depend in some way on the dimension of this tank. Okay. It could depend in some way on the dimension of this tank. Okay. And then it has to depend upon the fluid properties, because this drag force is exerted due to the fluid flow around the particle. Okay. Therefore, the drag force has to depend upon the fluid properties. Okay. First thing, it will of course depend upon the velocity. Okay. You would expect that as the particle moves faster, there is going to be a greater drag that tends to resist its flow. Okay. So, it should depend upon the velocity, but it should also depend upon the fluid properties. What are the fluid properties? Mechanical properties of the fluid are two in number, that is, one is the density and the other is the viscosity. Okay. After all, it is the viscosity that causes the resistance to flow. Okay. The frictional force is due to the fluid viscosity. Okay. So, it could depend upon the density and the viscosity as well. While enumerating these dimensional groups, one has to be careful. Okay. The particle density, for example, does not affect the drag force. Okay. The drag force is due to the fluid flow around the particle. Okay. And for the fluid flow around the particle, the only relevant quantity is going to be the fluid density. Okay. Similarly, the acceleration due to gravity does not affect the drag force. that is a separate force in itself. Okay. That is a separate force in itself. Okay. That is what we call a body force, okay, a force that is exerted on the body. It is proportional to the volume of the material or the mass of the material. Okay. Whereas the drag force is due to a surface force, okay, due to the force exerted on the surface of the particle due to the motion of the fluid. Okay. So, therefore, the acceleration due to gravity, for example, cannot affect this drag force. Okay. And by and large, this is the total dimensional quantities that can affect the fluid drag. Okay. Now, how do we find the form of the drag force? Okay. So, in this problem now there are how many dimensional groups? There is of course the dependent dimensional group, the drag force, and then there are the independent dimensional groups. Okay. I have 1, 2, 3, 4, 5 of them. Okay. The diameter of the particle, the dimension of the tank, the velocity, the density and the viscosity. Okay. So, let us list out all of these and look at what are the dimensions in these. Okay. The drag force is of course a force. Okay. It has dimensions of mass, okay, length t to the minus 2, okay, mass times acceleration. Okay. That is the drag force. Okay. The diameter of the particle and the length of the dimension of the tank both have dimensions of length. Okay. The velocity of course is distance moved per unit time. Okay. The density is a mass per unit volume, okay, mass per unit volume, and we had seen what is the dimension of the viscosity, okay, mass length inverse T inverse. Okay. We got that by from the Newton's law of viscosity, stress is equal to the viscosity times velocity difference by time, and that is how we had got this dimension. Okay. So, I have 1, 2, 3, 4, 5, 6 dimensional variables, and how many dimensions are there between all of these? There is a total of 3 dimensions, mass, length and time. Okay. And therefore, I should be able to get a total of 3 dimensionless groups, okay, from these, okay, from 6 dimensional variables and 3 dimensions, there are a total of 3 dimensionless groups. Okay. One of them is an independent dimensionless group, I am sorry, one of them is a dependent dimensionless group, because it involves the dependent variable, the drag force. Okay. Drag force is the dependent variable that depends on the other quantities. Therefore, one of them is a dependent dimensionless group, and the other 2 have to be independent dimensionless group, which just contain the properties of the fluid, the particle diameter, the velocity and the length of the tank. So, how do we get the dependent dimensionless group? Okay. So, for that I have to scale the force, okay, which has a mass dimension in it, with either the mass, the density or the force which has a mass dimension in it, with either the density or the viscosity, okay, combined with the velocity and the length scale. Okay. I can choose either of these, both are valid choices. Okay. I will come back and tell you in which cases we should choose the density and in which cases we should choose the viscosity. Okay. But at this stage both of these are valid choices. Okay. In this case I will choose the viscosity, okay, as the independent variable. So, I will construct a dimensionless group, okay. I will call it as the dependent dimensionless group containing the force non-dimensionalized by suitable powers of the viscosity, okay, the length scale, that is the particle diameter, okay, and the velocity, okay, to some powers. Okay. We do not yet know what powers these are. We will find that out by dimensional analysis. Okay. So, if this is a dimensionless group, then it has to have dimensions of mass power 0, length power 0, time power 0. Okay. It should be dimensionless. Okay. So, force has dimension of mass, length t to the minus 2. Okay. Okay. The viscosity is mass, length inverse t inverse power A, okay, length power B, and length t inverse power C. Okay. So, this combination of quantities has to have a net 0 dimension. Okay. So, if I look at the mass dimension in all of these, okay, then I will get one relation, that is 0 is equal to 1 plus A. Okay. If I look at the length dimension in each of these, okay, I will get 0 is equal to 1, okay, minus A, okay, plus B, okay, plus C. Okay. And finally, if I look at the time dimension in each of these, okay, I will get 0 is equal to minus 2 minus A minus C. Okay. Now, I have 3 equations for 3 coefficients A, B, and C, and you can solve these. Okay. The solution is quite simple. Turns out that A is equal to minus 1, B is equal to minus 1, and C is equal to minus 1. Okay. So, that actually satisfies these 3 relations. Okay. Therefore, my dependent dimensionless group, okay, is going to be equal to f d by mu u times the particle diameter. Okay. So, that is the first dimensionless group that I have had, that is the dependent dimensionless group. Okay. It is a scaled force, okay, scaled by suitable quantities in such a way that it ends up being dimensionless. Okay. Now, I should have 2 others independent dimensionless groups. Okay. One of them is quite easy to see. Okay. One of them is quite easy to see, since I have 2 lengths in the problem, the particle size and the length of the tank. Okay. The second dimensionless group, okay, is simply going to be equal to d by L. Okay. And I have to have a third dimensionless group which does not involve the drag force, but involves all the other quantities. Okay. And in this dimensionless group, okay, I can of course set any one quantity to the first power, okay, without loss of generality, okay, because regardless of which quantity is set to the first power, I will still get a dimensionless group, and the dimensionless group to any power is still another dimensionless group. So, it is a valid way to do things. Okay. So, I will just choose the density to the first power, because we have not yet used it in any of our calculations. Okay. So, the dimensionless group will contain the density to the first power, okay, the velocity to the power of A, okay, the particle diameter to the power of B times the viscosity to the power of C. Okay. Once again, mass power 0, length power 0, t power 0, okay, is equal to the density has dimensions of mass L power minus 3. Okay. U is L T inverse power A, L power B, okay, and viscosity is M L inverse T inverse power C. Okay. Once again, if we take the dimension of mass on both sides, okay, you get 0 is equal to 1 plus C. If we take the dimension of length on both sides, okay, you will get 0 is equal to minus 3, okay, plus A plus B minus C. Okay, so, I should put this also there. And if I take the dimension of time on both sides, I will get 0 is equal to A, okay, minus, yes, I am sorry, minus A minus C. Okay. And these are also simple relations and they can be solved quite easily. Okay. You will find that C is equal to minus 1, A is equal to plus 1 and B equals plus 1. Okay. So, therefore, this dimensionless group, okay, pi 3 rho u L by u. Okay. Okay, many of you will recognize this as the Reynolds number. Okay. We will come back to the physical interpretation of this, okay, dimensionless group. Okay. So, now that we have done this, okay, we can write this functional form that I had earlier. Okay. This functional form that I had earlier, okay, which involved a total of 6 quantities, I can write it to involve only a total of 3 quantities. Okay. So, what I will write is that f d by mu d u, okay, is equal to some function, okay, of d by L and rho u d by mu. Okay. So, that has greatly simplified this relationship now. Okay. So, you do not have to vary 6 quantities independently to find out what is the drag force. You just need to vary 3 dimensionless groups. Okay. Now, if the tank is much larger than the particle diameter, okay, if the length of the tank, okay, if length is much larger than the particle diameter, then you would think that the size of the tank does not really matter. Okay. If you have a very small particle that is settling in a huge tank, whether the tank is, if you have a particle of about a millimeter settling in a tank, whether it is 1 meter or 10 meters, it does not really matter. Okay. So, for a particle settling in an infinite fluid, this simplifies still further. Okay. F d by mu u d is equal to some function of rho u d by mu alone. Okay. So, we have reduced it even further to just one relationship. Okay. Now, what is the physical interpretation of rho u d by mu? Okay. This, as you know, is the Reynolds number. Okay. It has the fluid density in the numerator and it has the fluid viscosity in the denominator. So, it is some ratio of the fluid inertia and the fluid viscosity. Okay. If the Reynolds number is small, okay, if the Reynolds number is small, then the fluid inertia does not really matter. Okay. So, therefore, the fluid inertia is not an important parameter and the drag force should depend upon the viscous forces alone. Okay. So, therefore, density should no longer be important if Reynolds number is much smaller than 1. Okay. Okay. Density is no longer a parameter because it represents fluid inertia. Okay. Therefore, the result that I will get is that in this limit f d by mu u d should just be equal to a constant. Okay. If the fluid inertia is no longer important, the drag force divided by the viscosity, the velocity and the drag coefficient is just equal to a constant. So, we could even get the form of the drag force just based upon dimensional analysis if fluid inertia is not important. Okay. Of course, beyond this you cannot actually determine the value of the constant. Okay. If you actually wanted to determine the value of the constant, you would have to actually solve the problem. Okay. Find out what is the fluid flow around this particle. Due to that fluid flow, what is the stress that is exerted on this particle. Okay. That stress summed up over the entire surface will give you the net force that is exerted. Okay. And that is an elaborate calculation which will be a little bit advanced for this course. But at the end of it you find that the result is that f d by mu u d is just equal to 3 pi. Okay, you can do that calculation analytically. Okay, and this is what is called the Stokes-Drag law. Okay, Stokes-Drag law for the drag force exerted on a particle in the limit of where the fluid viscosity is much larger than the fluid inertia. Okay. And this kind of a Stokes drag law actually gives you the correlation for the drag coefficient, which I was talking about in the last lecture. Okay. I told you that we expressed dimensionless groups in terms of ratios of dimensionless numbers such as the Nusselt number, the Sherwood number and so on. For momentum transfer, the appropriate groups are what are called the drag coefficients. Okay. And in this case, the drag coefficient is defined as, let me get rid of that. For the flow around a particle, the drag coefficient is defined as the drag force divided by the projected area by half rho u square. Okay. Where the projected area is the area of projection, okay, the area projected by the particle to the fluid. Okay. So, we know that the projected area, okay, the drag force is 3 pi mu u d, okay, from the Stokes drag law. Okay. The area of projection is pi r square, which is pi d square by 4, okay, divided by half rho u square. Okay. And if you use this, you simplify this, you will find that this is just equal to 24 by rho u d by mu is equal to 24 by the Reynolds number. Okay. So, that is the first correlation that we have got, okay, for the drag coefficient on a sphere settling in a fluid, okay, when it satisfies Stokes drag law. Okay. So, these are often plotted in log-log graphs, okay, the drag coefficient versus the Reynolds number. Okay. And this drag coefficient is valid, as I said, at low Reynolds numbers. As you increase the Reynolds number, the flow becomes more complicated, okay, and the drag coefficient tends to some constant value. Okay. But this is in the limit of low Reynolds number. Okay. As the Reynolds number increases, this f d by mu u d, okay, does depend upon the Reynolds number. That Reynolds number dependence is a little complicated, and I will discuss it when we actually do momentum transfer around a sphere. Okay. So, this is the simplest example. Okay. We have done dimensional analysis, but a little bit more. Okay. We said that when this number is small, we can neglect this as a parametric dependence, because the tank volume is much smaller, much larger than the particle size. And then we can look at different limits where the Reynolds number is large or small. Okay. When the Reynolds number is small, I said that we can neglect density altogether and we get back the Stokes drag law. Okay. When the Reynolds number is large, can we neglect viscosity altogether? Simplistically, you might think that let us just neglect viscosity and solve the rest of the problem. However, as I said, the momentum transfer is due to the stresses exerted by the fluid on the particle surface. The stresses exerted tangential to the surface are entirely viscous, okay. And therefore, even when inertia is large, you may not be able to neglect the stresses exerted on the surface, okay, and we will look at that in a little bit more detail a little later. Okay. So, this is the simplest example. Okay. Let us take the next more complicated example, and that is the heat exchanger problem. Okay. I will just introduce the configuration of the present class, and then we will continue this in the next lecture. Okay. So, we have a shell and tube heat exchanger. in this case we will consider that there is hot fluid coming in, cold fluid going out. Okay. This is being cooled by a coolant that is coming in through the shell side. Okay. Now, in this case what we would like to know is actually what is the total heat that is transferred, okay, across the tube wall. Okay. But this heat that is transferred of course depends on the length of the heat exchanger, the diameter and so on. So, what is normally done is to define an average flux Q, okay, average flux across the tube wall, okay, that is the amount of heat that is transferred per unit area per unit time. Okay. So, whereas the fundamental quantity here is the heat exchange itself, the rate of heat exchange, the heat that is transferred per unit time across the wall. We express this in terms of an average flux, which is the total heat transfer divided by the area. Okay. Obviously, there is a more convenient way to do it, because as you keep increasing the area, simplistically you would think that the flux has to increase. Okay. And that is going to be a function of the average temperature difference. Okay. Okay, it is going to be a function of the average temperature difference between the shell side and the tube side. Okay. But it is more than that. Okay. It also depends upon other quantities. It depends upon the thermal properties of the fluid, okay, the thermal conductivity, the specific heat. Okay. In addition, the heat that is being transferred is being swept into the tube due to the fluid flow itself. Okay. And so, if I look at a differential volume close to the surface, okay, there is fluid that is flowing across the surface, carrying the heat with it as it flows, and that has to diffuse through the surface to the other side. Okay. So, in addition to the thermal properties, the mechanical properties of the fluid will also be important, okay, the density, the viscosity and so on. Okay. In addition, these properties are also important for determining what is the pressure difference between the ends of the pipe, okay, which is also an important design consideration. Okay. So, on the basis of dimensional analysis, can we get some idea of what are the dimensionless groups, okay, rather than the dimensional parameters that affect this transport process. Okay. And once we know what are the dimensionless groups, we can then try to get relations between these dimensionless groups. Okay. So, that we will continue in the next lecture. Next lecture I will give you a dimensional analysis of the heat transfer in a heat exchanger. And then we will go back and look at the other problem that we had looked at in the introductory lectures, and that was the mass transfer from a spherical particle. Okay. And then I will give you some physical insight into the dimensionless numbers that arise in these kinds of transport processes. So, we will continue this in the next lecture, and I will see you then.